Hey folks, welcome to this episode on ionic bonding and properties. So what is ionic bonding? Well, remember, it's the complete transfer of valence electrons between two or more atoms with varying electronegativity values. And it's usually a transfer from something that has a low electronegativity to something that has a high electronegativity. Now remember that something that has a low electronegativity is usually a metal, and something that has a high electronegativity is a nonmetal. So effectively, there's a transfer from a metal to a nonmetal. What the nonmetal does is it rips away the electron because of these differences in electronegativity, and they both satisfy their octets. Now what happens is that the metal turns into a cation, and the nonmetal turns into an anion. And there's an attraction between these opposite charges. This attraction is called an electromagnetic attraction. How do we form ions? Well, remember, it's all about the ratio between protons to electrons. Now, when we look at chlorine has 7 valence electrons here in the outer shell. It needs that one more. So it's going to pick up an electron and form our chloride ion. So what we see here is that it still has the same number of protons. Remember that protons are the identity of that element. We're not going to change those amount of protons. But what we can do is change the value or the amount of electrons that they have. Here we have 17 plus. And here we have 18 minuses. So what our net overall charge is going to be 1 minus. So this is going to have a bracket here saying 1 minus. Now the question is, where does it pick up this electron? Well, remember that if it has an interaction between sodium, which is a metal, which wants to lose that electron, it's going to pick that electron up from there. So if sodium loses an electron, again, it still has the same amount of protons, but it has one less electron. So this is going to form a cation of 1 plus. Now, because these are opposite charges, this negative is going to interact with that positive, and you're going to have an ionic bond. The reason it's ionic is because you have a full negative charge and a full positive charge created through the transfer of electrons. So again, here we see a little kind of Bohr-Rutherford diagrams to show this interaction. Again, Lewis structures are favorable because we don't really need all these inner electrons here. So in this case, again, sodium is going to be losing that outer electron here to chlorine, and you can see that it picked up over there. That creates a cation, that creates an anion for chlorine, or chloride in this case, and you're going to have an attraction between the positive and the negative. Again, sodium is a metal. It's going to have a low electronegativity, while chlorine is a nonmetal, and it's going to have a high electronegativity. This doesn't want the electron so much, this wants the electrons. Not only that, but this has a low ionization energy, which means that it doesn't take a lot of energy to strip away that electron over there. Now, if you remember about ionic formulas, and we did this at the beginning of the year, and we have calcium and phosphide. Remember how to create that formula. We have Ca and we have P. We find the charges on the periodic table. Calcium is in group number 2, so it has 2, and it's plus because it's a metal, it's going to lose electrons. And phosphorus is in group number 5, so it has 5 electrons and it needs to pick up 3, so it's going to gain 3 minus. We cross, and we get Ca3P2. Now, how do we actually get that formula? Through the interaction of electrons. Well, I'm just going to create a little list here. Let's start off with calcium. Calcium is in group number 2, which means that it has 2 valence electrons. So it has 1 and it has 2. Phosphorus, on the other hand, is a nonmetal, and it's in group number 5, so it will have 5 valence electrons. Now, in this case, phosphorus needs to gain 3 electrons to get that full outer shell. Now, where's it going to get it from? Well, if you guessed calcium, you are right. So calcium will give off these 2 electrons, and itself forming Ca2+. Now, the problem is that phosphorus still has space for 1 more electron. Where's it going to get it from? Well, if you guessed calcium, that is correct, because calcium wants to give away electrons, and if we have a sample of both, calcium will be glad to give away its electron. In this case, it'll go right there. So what we've created here is we have P3 minus with its full outer shell. We have 1, 2, 3, 4, 5, 6, and 7, 8. The problem now is that when we look at calcium, calcium has this unpaired electron that it wants to give away. Who is it going to give it away to? If you guess phosphorus, again, awesome job. Here, phosphorus has our 5 valence electrons, and it wouldn't mind giving it away over there. Now, when this happens, again, calcium is going to lose all of its electrons, so it becomes calcium 2+. If you see the problem here, Phosphorus has 2 unpaired electrons. Now, where is it going to get those electrons from? Here's our trusty calcium again. Calcium has 2 electrons that it doesn't mind giving away. So what we're going to see is that it gives away this electron here and that electron here. When it does that, again, we're going to form calcium 2+, and phosphorus will form another 3-. 3- because it has 8 valence electrons now. So now all the phosphorus atoms are satisfied, all the calcium atoms are satisfied. So let's do a tally here. What we see is that we have 3 calcium atoms, 3 Ca2+, and we have 2 phosphorus atoms, 3-. Well, look at that. Look at our original formula. There's 3 calcium atoms and 2 phosphorus atoms. So if we were to write this in a different way, we get Ca3P2. Now that formula that we just created is called a formula unit when we're talking about ionic bonding, because an ionic structure actually forms in a kind of crystal. So they have a constant repeating pattern. And so it's impossible to create the molecular formula or a complete formula for this whole crystal because it actually is not limited by size. So what we do is we create a formula of a common repeating pattern. In the case of sodium chloride, NaCl, we have a constant repeating pattern of NaCl beside an Na, beside a Cl. So we call this our formula unit of NaCl, and it's the lowest whole number ratio of atoms in that compound. So once again, ionic compounds, they exist as this lattice, which also is called a crystal. In this case, when we talk about ionic compounds, we can use Lewis dot diagrams and arrows to show the transfer of electrons between atoms. So when we look at magnesium and iodine, so we're going to have two I's here, just to make things a little bit easier. So our magnesium, again, it's in group number 2, we'll have 2 valence electrons, and our iodine, well, 1, 2, 3, 4, 5, 6, 7. And it's a halogen, it's going to have 7 valence electrons. Well, why is there a 2? Well, let's look at this. Magnesium wants to lose these 2 electrons. Well, iodine only has 1 spot. So how are we going to get another one? Well, we're going to have another iodine. Okay, so iodine again has 1, 2, 3, 4, 5, 6, 7. And so magnesium will gladly give away its electron to this iodine, which is why we have the coefficient of 2. So if we get this here, what's going to happen is we're going to have Mg, and it's going to have brackets, 2 plus, and we're going to have 2 iodines that have a full outer shell. Each of them have a negative charge. And make sure we show the number of valence electrons there, 1, 2, 3, 4, 5, 6, 7, and 8. So we've shown our Lewis structures. We can see that we have magnesium with 2 electrons. We have an iodine and an iodine. We could short form it by just putting 2 iodines to create magnesium cation and 2 iodide anions. These are different graphical representations. We could use a Bohr-Rutherford diagram to show this transfer of electrons. We can show the Lewis structure using all of our valence electrons, or it could simply be in a balanced chemical formula as seen over here. Some properties of ionic compounds. Like we mentioned before, they form crystalline structure called lattices. And so again, there's these kind of repeating formula units throughout. They have a high melting point and high boiling point because the ionic bond is actually quite strong. So you need a lot of energy to break those intramolecular forces. And most ionic compounds dissolve in water. Now we're going to be talking about them. We don't say all of them because there are some that actually don't. And when we get into our solutions unit, we're going to be looking at some rules to help us decide whether or not they're going to dissolve in water. Now, they're also hard and brittle, which is a very interesting case. When we look at here, here we have an ionic salt or ionic lattice, and we can see that we have these repeating blocks, positive, negative, positive, negative. And if we apply a force on this, what we're going to be doing is we're going to shift this whole side down. Now, what you see is that here, as we put that force on it and we shift it, what we can see is that these positives are beside another positive, and these negatives are beside another negative. Now, what do we know about like charges? Well, they repel. When they repel, we're going to have a crack in the crystal. In terms of chemistry terms, it is called a cleavage. And here it also conducts electricity when it's dissolved or in the molten state. It doesn't conduct as a solid. So if you actually try to put a wire in a block of of salt, okay, and kind of hook it up to a battery and then hook it up to a light bulb, what you'd see is that you wouldn't have any kind of light coming through there. But if we were to dissolve it, what we'd create is we'd create these ions. And when you apply a charge, you can actually, well, basically what happens is that you can apply a charge to these ions, the ions can carry that charge, and you're going to get conduction of electricity. Now, when you dissolve a ionic salt in water, it does dissolve, if it's one of those that dissolve, and it creates something called an electrolyte. Now, you may have heard this. It's found in sports drinks. It's also found in your body and things like batteries to kind of power your flashlight there. An electrolyte is something that gives off ions when it's dissolved in water. So, for example, if we had NaCl solid and we dissolved it in water, what would happen is it would split up into Na plus aqueous, which shows that it's dissolved in water, and would create a chloride ion, again, aqueous. And so both of these, when it's dissolved in water, exist as ions, and those are called electrolytes. Things that give off ions, they could be acids, bases, or salts. Acids generally give off H plus ions, again, aqueous because it's dissolved in water. Bases, at least classical bases, give off OH, again, aqueous because it's dissolved in water. And salts, they could be a whole number of different salts, but could get off some metal ions like sodium plus, magnesium 2 minus, or can give off some nonmetals like chloride ion or fluoride ion, etc. They conduct electricity because of the mobility of the ions, and again, we can find them in our body. It's interesting, if you look at this periodic table at the bottom here, these are all the ions that are essential for human life. You can have these ones that might be suggested as essential. Maybe there's some more research that needs to be done, but you can see that there are quite a bit essential ones for our daily existence. Okay, so you can take a look at this summary of ionic in terms of the electronegativity and ionization energy, and finally a chart of its properties as a summary. You can see that we're going to go through these and a little bit at a time, so we can have a final kind of overview of all these different properties. Thanks very much, guys. See you soon.